everyone, and welcome to today's GEN webinar. It's entitled An Automated Process Analytical Technology-Driven UFDF Process. Our webinar was made possible through sponsorship from Repligen. I'll be your host today. I'm John Sterling, Editor-in-Chief of Genetic Engineering and Biotechnology News. GEN has been the leading source of information on new tools and technologies for the life sciences industry for over 40 years. Today's webinar will discuss an innovative integrated system designed to automate the tangential flow filtration process based on inline concentration measurement. This system employs inline variable path length spectroscopy to acquire concentration measurements and to enable real-time monitoring and control of the process and ensure desired results. The system's automated process control capabilities are demonstrated across a range of final concentration endpoints. Data presented in the webinar are highlighted to illustrate superior performance compared to traditional ultrafiltration, diafiltration methods. Our presenter is going to talk a lot more about this and other capabilities using this approach. So let's meet him now. Derek Carroll is Director of Research and Development at Repligen, a bioprocessing-centered life sciences company that is focused on bringing expertise and innovation to its clients since 1981. Derek is a certified project management professional. He holds a bachelor's degree in mechanical engineering from Colorado State University and a master's degree in biomedical engineering from Cornell University. Before we start our webinar, I want to remind the audience that there will be a live Q&A session that will begin right after the presentation ends. Derek will be available to answer as many of your questions as he can. So simply type your questions into the question and answer box and hit submit. So if everyone is ready, Derek, please go ahead and begin your presentation.
All right, hi, my name is Derek Carroll. I'm going to be presenting today on an automated PAT-driven TFF system that's using inline concentration monitoring to control and expedite your UFDF process. We'll go over some of the market needs and challenges that prompted the development of this product, go over some of the system highlights of the product that's now been developed, do a technical overview and look at some of the data that's been generated, and then at the end we'll have a Q&A. So Repligen has been transforming bioprocessing with a lot of high impact technology innovations. We have our upstream process intensification with Excel ATF and our KrosFlo TFDF. We have our high yield chromatography with our Opus columns and Chrome systems, as well as our Avipure affinity resins and ligands. We have scalable filtration and formulation products with our TFF systems, hollow fiber filters, and flat sheet cassettes. And then we also have secure fluid management with our ProConnex standard and custom flow pass, single-use containers, and valves and clean room equipment. We also have real-time in-process analytics. So that is CTEX variable pathlength spectroscopy, with the two main products being the Solo VPE and the Flow VPX. And what we'll be discussing today is the unification of those real-time in-process analytics and our scalable filtration and formulation platforms. So when we were looking into the biggest areas of interest for new product development, what we saw was real-time inline product sampling and testing, automation instrumentation, continuous bioprocessing, design of experiments, PAT, analytical assays being the top 5 most biggest areas of interest. And we really are now looking at trying to bring all of those things together with real-time sampling that is allowing for automation control. This could enable in future iterations of the product continuous bioprocessing, and so really addresses the major market needs. We've also seen there's been a move in the industry towards higher concentration MABs in that greater than 100 mg per mil range. And this is very well suited to this with CTEX variable pathlength technology. We're able to measure and get readings well above 100 mg per ml up to the 2 and even 300 mg per ml range. So it's very well suited for the direction the industry is going for higher concentration mAbs. We have also looked into some other applications. So if you are not working with mAbs, you're working in gene therapy type of applications, we have done a variety of others as well. So we can, in many cases, measure concentration and control processes using inline analytics. So in a typical TFF process for UFDF, it's a CDC we call, which is a initial concentration followed by a diafiltration and then a final concentration up to the final goal of the formulation. So typically how that's gone is there would be an initial concentration determined offline. Then there would be a mass balance calculation for what concentration factor we would need to go to for the initial concentration. Then during the diafiltration stage, a certain number of dia volumes are set. And then again, going to a final concentration factor for the target. And then there's another offline protein concentration that's determined. Ideally, that will match up very closely with your goal. If not, there might need to be some dilution if there's overconcentration or even secondary processing if there needs to be further concentration. So that is mass dependent. So it really requires accurate measurements from load cells. It's fragmented, so there will be different data sets in different areas. So your automation equipment will have weights and record the process that took place there. Then you'll have your offline concentrations. You need to come and match those up after the fact. So there is a high level of variability, and there's also a risk of what I would consider more gross errors. If there's hold-up calculations that are incorrect, requires dilution steps, which are adding error. There's many opportunities for human error with potentially incorrect tearing of scales. So it really does require a high amount of skill and is very sensitive to those kinds of inaccuracies. So our new system that we've developed to address a lot of these concerns is a combination of two product lines that Repligen has had in its portfolio for a good amount of time. So it's the CTech Flow VPX system. This is an inline uv-vis spectrophotometer that uses variable pathlength technology. And then the KrosFlo KR2i system, which is our small scale TFF automation system, very common for use in lab scale UFDF types of processes. Those have now been unified with a common software platform that we're calling the RPM for real-time process management. So for the Flow VPX specifically, there's rapid data acquisition. It generates 12 QC grade concentration measurements in 1 minute and has continuous data acquisition throughout the entire process. There's a very broad dynamic range for concentration measurements across the entire length of adjustable path length, all the way down to 0.1 mg per ml up to 300 mg per ml, can all be measured in line without any need for dilution. So it allows for much better accuracy for doing your measurements. It doesn't require it going offline and performing dilutions to avoid saturating the signal. So how this works, you compare to your traditional UV spectrophotometers. What that would be, typically there's a cell that you would add your sample to. The path length is fixed for a particular cuvette. You would then need to prepare dilutions for making sure that you don't saturate the signal. And then you can go back and reapply those dilution factors to calculate your actual concentration. With variable path length spectroscopy, it now unlocks path length. So you put your sample directly into a sample vessel, or in the case of the inline, you pass it through the flow cell. the path length is now a variable, and it will adjust that to find the value that is not saturated, so you don't require any dilution to measure concentration. So for a inline type of measurement, you can actually plot and collect data over time. So in this example, in this graph, a typical UFDF run, you can see over time, you can measure your concentration as it goes up during the initial concentration, stays flat as you do your diafiltration stage, and then final concentration reaching the final set point of the process. So the KR2i, the other piece of the automation, is our what we call walk-away automation with 13 automated process control modes. Can also be operated manually and allows robust processing from volumes 10 milliliters all the way up to 10 liters. So really a great tool for any TFF types of operations you need to do at lab scale. Minimizes risk with fully enclosed ProConnex custom flow paths. These can include Repligen hollow fiber filters or flat sheet cassettes. And it's also a flexible configuration. So depending on what kinds of accessories, what kinds of sensors you might want to use, it is a plug and play platform for flexibility for whatever process you may be running. Okay, in the technical overview, we'll get into some of the data, but the first thing to look at maybe is the setup. So if we were to look at a typical UFDF run, this is an example where we're setting up and doing a CDC type of run. So that would include a buffer tank that is fed by a diafiltration pump. There's a feed tank with a feed scale. We have our back pressure control valve on the retentate line, and then sensors monitoring pressure on the filtration. What's different about this is you'll see the Flow VPX now in line. So that is right at the outlet of the feed tank. So that is the most representative of the overall concentration of the entire sample or the entire process fluid. So you can determine what the concentration is in the feed tank by placing it just at that outlet right before it passes through the feed pump. So the software itself, so this is our PAT-driven TFF process, the RPM software. So it allows TFF automation control based on inline concentration. We do now have multi-wavelength feature coming in a new launch this fall. It provides real-time overview at every step of the filtration process. It will automatically graph, trend all data, record every aspect of the run. And again, it does allow flexible plug and play for whatever your custom needs may be for a given setup or a given process. All right, we'll get into an example run. So in this run, this is a UFDF run, CDC. You can see in the configuration of the recipe, you can actually select either permeate scale or VPT device. In this case, since we want to control the concentration stages based on the readings by the Flow VPX, we select VPT device. Then we choose our endpoint as a protein concentration, and we can actually directly input what concentration we want for diafiltration and as well for the end of the process. So in this case, we're targeting 38.5 mg per mil, 4 dia volumes, and a final concentration of 150. So in this setup, we can see when we start the run, in this case, there is a additional feedstock that is pulled in by vacuum. The recirculation vessel will maintain a constant volume as that is pulled into the process. And you can see in the graph in the top left, your concentration is starting to increase. As the feed vessel drains, you can see an inflection point where the concentration speeds up, and then it continues all the way up until it reaches that set point. Then as we go into the diafiltration stage, buffer is added. So the pump here, the diafiltration pump is adding buffer to the recirculation vessel. You can see the levels being maintained. And you can also see that the concentration is flat throughout this stage as it's not actually concentrating the target molecule. And that continues until the prescribed number of dia volumes are met. Then in the final stage, it will continue to draw down. You can see it's starting to get fairly low on the volume as it starts to climb very quickly. And then it will continue all the way up until the point that it reaches the final concentration that was input, 150 mg per ml. All right, and one more run that I wanted to include to illustrate the capabilities of this system. So ran side by side, very similar process, one with mass balance targets, another with inline analytics targets. So in the mass balance targets, we're using what I described more traditional method, using concentration factors, diafiltration volumes for a CDC process. And then for inline analytics, we're using the VPT device for concentration. And also in the diafiltration step, we're using conductivity instead of a prescribed number of dia volumes. We would look at the output of these experiments. You can see a comparison between, in gray is the mass balance, in blue is the inline analytics. And you can see on the left axis for protein concentration, the inline analytics very closely meets that, and it maintains it throughout the diafiltration stage, where the mass balance overshot it slightly, still maintained it well during diafiltration, and then again over concentrated near the end, where and again, the inline analytics is now allowing you to not have to do any secondary processing. So if we were to look at this example, this is the kind of scenario where you would need to do a secondary dilution to get you back down into your target after the run was over. With the inline analytics, no need for that. On the other axis on the right, you can also see the conductivity. It actually, in this scenario, it reaches the target for conductivity, showing that the process is complete. It's exchanged the two buffers, and there's really no need for the extra diafiltration volumes that are put through. So that would also save time, save buffer if someone were to use inline analytics versus mass balance. Also in this experiment, we did comparison showing consistency across spectroscopy platforms. So taking comparison of the Flow VPX, Solo VPE, and also fixed path length. And we took them at 3 stages: the initial concentration, the end of diafiltration, and then the final concentration at the end. And we see good consistency across the different platforms. So we see this integrated solution for lab scale development as really being the first stage in our journey of bringing together inline analytics and our automation systems. So currently launched is the KR2i TFF system with a peristaltic pump. This fall, we are also releasing the FS15, which is a diaphragm pump as well. So that will also be available. And then the intention is to continue this journey through all of our larger scale systems and bringing it to all of our technologies that may benefit from this kind of inline process monitoring. We also have all of our additional Repligen products to drive a seamless process. So you can marry this together with our hollow fiber filter modules, flat sheet cassettes, our single-use flow paths, both standard and custom, and all the components, equipment, reservoirs that you may need for your process. All right, so with the KrosFlo KR2i RPM system, you can strengthen your process control with high quality and highly reproducible results, increase process efficiency, reducing cycling time, increasing yield throughput, and reduce risk of inaccuracies throughout your process. All right, I think we have time for some questions.
Derek, thanks for that great presentation. Your discussion on this new path-driven tangential flow filtration system clearly demonstrated how the approach represents a significant advance in ultrafiltration diafiltration technology. Thanks again. The Q&A is coming up in a few moments. If anyone has a question for Derek, just type it into the Q&A and then hit submit. And we'll take a look in just a few seconds. I have a good number of questions, and we'll try to answer as many as possible. So bear with us while we bring them up. Okay, Derek. So the first question is the addition of DF buffer to be used manually by the one putting the run on, or is it an automated calculation based on concentration input output?
So it's not manual. It is still automated, but it's not based on concentration. So it's the way traditional mass balance, it would still maintain a constant volume in the feed vessel as it pulls in the buffer addition for the diafiltration step.
Okay. And another question, does the VPX use disposable pipettes? Have you seen issues with protein absorption onto the probe during processing, and can this be removed by CIP?
I wouldn't consider them disposable. They're multi-use, but they are replaceable. So if they did need to be replaced, just that single item could be replaced. There could be issues with protein absorption if it's not cleaned thoroughly afterwards. We've seen that kind of thing before. But if you flush with sodium hydroxide after the run, do a cleaning step, it would be ready to go for another run, and they are reusable.
So flushing it with sodium hydroxide will do the trick.
Correct. Yep.
Okay, good. So is the TIF in an optimized PD, and what are the limits of sample in terms of viscosity, solid content, percentage-wise, and protein concentration?
Okay, so I'll start with the protein concentration. So the limits in terms of protein concentration mentioned in the presentation, actually, we give a range of about 0.1 mg per mil all the way to 300 mg per mil. That is a little bit dependent on molecule, but generally that's a good rule of thumb for that range. Viscosity, we don't see any sensitivity to viscosity. We've done a good amount of trials, even with very viscous solutions or not so viscous solutions. We are still seeing very consistent results. And then in terms of solid content, we haven't really seen too big of an effect. If there is some kind of scattering of the light due to the solid content, we may address that through a built-in scatter correction. So that is also an option if we do see that scattering.
Okay. And another question from the audience. Do you have to input an initial offline reading of protein concentration conductivity before initiating the CDC program?
You don't, no. So it's purely based on how it measures the absorption prior to the run and the extinction coefficient that you give. It will do the calculation based on the absorbance reading. So there's no need to calibrate it with your starting material. You can just go ahead and place it directly on from the beginning of the run. Similar with conductivity, actually. So there's a K factor for each individual sensor that is calibrated when it's manufactured. You input that K factor and it will start giving conductivity readings from the beginning of the run. There's no need to calibrate that prior to running.
Okay. And another one here, during the DF step, do we need mixing?
Generally, I would say yes. So there's passive mixing that maybe you might not need active mixing. And when I say passive mixing, just through the nature of a TFF process, you're recirculating your material. That might be enough that you don't actually need active mixing with impeller or stir bar. What's interesting about that question in the context of this equipment, though, is we really can actually see issues with mixing based on the readings that we get. So what do I mean by that? Maybe an example would be if there's polarization of your feedstock, you're starting to see it separate out. What that could do in a TFF process is create a situation where your more concentrated material is flowing through your TFF loop and the less concentrated material is just sitting above that, floating on the surface. And that can lead to issues because now you're you're concentrating very concentrated material instead of thoroughly mixed material. That can lead to things like aggregation, and it can actually be seen now with the Flow VPX. You can start to see concentration is increasing much faster than it should theoretically be able to. And that's something you'd be able to see in the charts. And there are also ways to configure the alarms where it would alert you to something like that happening, and you'd be able to intervene, potentially start active mixing and solve the issue, versus getting all the way to the end of your run. You're running a mass balance type of operation. Everything looks fine on the scales, but you get to the end of your run and it's not what you expected.
Mm-hmm. What's the highest flow rate? The highest flow rate Flow VPX can be used with? Are there different piping sizes that can be installed or on Flow VPX? And this person's thinking of production scale.
Got it. Yeah. So there's 3 sizes of flow cell. So there's a 3 millimeter, and that's really for this system generally what's most common for lab scale. There's also a 10 millimeter, which is somewhat common. Some of these larger scale processes getting 10 plus liter range, we would start to see more use of that size. And then there's also 22 millimeter. So that would be more for production size. Generally, we don't really think of the restrictions being flow related. They can run very fast flows. There are stainless steel designs, so there's not really any kind of restriction, and we can get pretty good readings. They are pressure rated, so pressure rated up to 80 psi. Generally, that's plenty for any kind of TFF run we would be using it on, but that would probably be the thing to keep in mind if you were trying to run very fast.
Okay. So another questioner says, we would like to use Flow VPX in the SPTFF ILDF step in the CM process. Does it make more sense to use Flow VPX in the feed line or in the SPTFF retentate line?
Got it. So single pass TFF. So this would be more for like a continuous type of process. So as the system's designed today, it's really intended to be used on batch processes. So it's when you're thinking about a recirculation loop and placing the Flow VPX on the feed line to get an accurate representation of what the batch is and how it's concentrating over time. That's the reason that we would put it there. That being said, there have been some applications we've looked into for continuous processing, single pass TFF with the Flow VPX. And in that case, it still made the most sense to look at it and the feed line, because the goal we were trying to accomplish was control of the TFF run parameters. So in terms of feed rate and back pressure control, to make sure that it's running at an optimal condition for whatever variation you might see in the concentration coming down the single pass, coming off the continuous line. So yeah, I would say it's still in that application makes more sense to put it on the feed line, but it does depend on what you're trying to accomplish. And I can see why it may be interesting as well to monitor the concentration coming off of it. But it really depends on what you're trying to accomplish and what you're trying to control.
Mm-hmm. And what's your minimum process volume using both Flow VPX and KrosFlo KR2i systems?
So the minimum would be, it's really related to flow path design more than anything and what size reservoirs you're using. So the KR2i system, using very small tubing, very small reservoirs, can get all the way down into the just a few milliliter range. I've seen as low as 1 milliliter with a hollow fiber filter with a very low holdup. So it is possible to really push that down to some very low volumes. The Flow VPX itself, the flow cell for the 3 millimeter, which is the smallest size, adds about another 0.9 milliliters. So, it depends on what you're doing. It depends on what filter you're using, what surface area that might be a limiting factor as well. But I'd say if you needed to get into just a few milliliters, it would still be potentially possible. It'd definitely be interesting to talk to your local Repligen FAS application scientists for some support. It may be very possible to achieve some very low volumes.
Okay, good. And can you control concentration to specific ranges with specified minimum and maximum?
So how it works in the software, it's a single point process. It's not really controlling to a certain range. But it would make a lot of sense that there would be some kind of spec that you would need to meet for your process, that you would have a minimum and maximum. Generally, I'd say in your PD work, you'd want to target a nominal, the midpoint in between your min and max. We do see in certain types of runs, depending on starting concentration, ending concentration, how much holdup volume is in the retentate where there's more concentrated material. We do see a little bit of variability. More often than not, it will overshoot more than undershoot because there is an amount of material that's in the holdup of the retentate line that is more concentrated, hasn't been able to run back in, be fully mixed out. But when we were doing development, we ran a number of DOEs exploring a very large range of process conditions. Generally, we found everything was in about plus minus 5%. And even maybe better than that, we found that the repeatability from run to run was extremely consistent. So if there was a particular set of conditions that was more likely to be on the high side, maybe a 5% over concentration, we would be able to maybe adjust for that, change the target, knowing where we were likely to end up, and then repeat the runs after that and find that we were very consistently hitting the same concentration run to run.
Okay. A point you brought up during the talk, and I want to pick up on it, said the system employs an inline variable path length spectroscopy to acquire the concentration measurements to enable real-time monitoring and control of the processes. There are a lot of forms of spectroscopy. Why is this particular form more suitable to what you're trying to do here?
So it's mostly suitable because of the ability to vary the path length. So there's been fixed path length spectroscopy inline that's been used for a good amount of time. And it's been very useful at monitoring things like breakthrough. So if there was any protein that was able to pass through your filter, for example, it would be able to detect that it was in the permeate. You're not concentrating, there's some kind of issue where your molecule is not being retained. But it's kind of more of a qualitative type of system where it's detecting whether something's present or not. When we go to the concentrations we want to achieve in a typical UFDF run, especially going to very high concentrations, as I mentioned also in the presentation, we're starting to see the industry go to higher and higher concentration targets. The signal will saturate with even with some of the smaller flow cells, smaller path lengths that you might see on the market for fixed path length types of technologies. Because of the ability of the Flow VPX to actually vary the path length in line, still using the same flow cell, but actually using that adjustment to the distance between the source light and the detected light, we're able to still monitor those very high concentrations in line. So that's the real difference that makes it suitable for now trying to get a quantitative measurement and taking that one step further, using it as feedback control for automation.
hmm So this process analytical technology approach that you use, and it's an industry standard that's been around for quite some time. Sometimes we think this is, at least we do, because we're not doing what you do, that it's fixed. And it's for new people coming in to understand what you need to do to carry out a certain bioprocess operation. So for your particular approach here where you're using this, do these regs or approaches or advice change from time to time where you need to adjust what you're doing accordingly? These things, in other words, it's called process analytical technology. I think sometimes those of us who don't do this for a living, we think of them as fixed, but I'm assuming for even what you're doing, sometimes they might change. And how do you keep up with that in terms of what's being required?
So are you saying in terms of using it as a control strategy versus,
Yes.
yeah, some more
Yeah.
traditional methods?
Yeah.
Yeah, we do see that for the most part, people are going to continue running their processes as they have. Where we're starting to see it take more of a foothold, and I think this will change over time. Um, I think that what we're seeing right now is it's a very useful development tool. So as you're in the lab running your PD types of runs and seeing what kind of run parameters we need to meet certain targets, right? So certain targets for, in this case, concentration. You can see specifically what you would want to do to structure your run. You can also use it to run DOEs to see what is the range of processing conditions that landed us at those target conditions based on lot-to-lot variability, that kind of thing. And then you could say, transfer that data, say, okay, here's the process still going back to the traditional way using mass balance. Here's the process that's the most robust that we can take into production. So we're starting to see a little bit of a foothold there. We're also seeing some of the newer therapies having gone through all the V&V very early stage, just thinking about how to develop processes around them, that there is a lot more interest, and maybe we're going to actually scale this process and use control all the way to the GMP types of situations. We haven't seen that yet, but we are still fairly early in that journey. But I could see a lot of advantages to doing that down the line. And it would just be a matter of doing your validations now with a different control strategy.
Yeah. Well, thank you for that. Just listening to you and came up, we use this term process analytical technology, and you just answered how it can change, how it can move, what are the new applications. So I appreciate this. Here, we're coming up to the end of the webinar. Is there any finer point you want to make on this very interesting system, which I think my readers are going to be and viewers are going to be very interested in?
Yeah, I mean, I think this is really it's an exciting new technology. I think it's the future in terms of how people are going to be running their UFDF processes. And it's really gives you insight into what exactly is happening versus, the more traditional methods where you're a little bit blind during the run. You don't really know exactly what's going on. And I think that's the real power of this technology.
Well, Derek, again, thank you so much for a really interesting and I think very useful information for a lot of Gen readers and viewers are involved in a lot of this type of work. So that was a most informative presentation. Thank you. I'd also like to thank you, the audience, for your attention and some very thoughtful questions. I want to remind everyone that this webinar will be archived on the Gen website. That's www.genangnews.com for up to a year. If you missed any parts of it, you can watch it again, or feel free to forward the webinar to any of your friends and colleagues who you think might be interested. And special thanks goes to Repligen for sponsoring this webinar. So until we meet again on a Gen webinar, thank you all for attending very much.